So integration allows to split addition of two functions to separate intervals. Okay, the proof and Sn dash. Okay, we do Sn dash. These sequences of non-negative simple measurable functions is that Sn increasing and converges to F1, Sn dash increasing and converges to F2. Then monotone convergence theorem, okay, implies that limit integral Sn is integral F1, limit integral Sn dash is integral F2. Sn converges to Sn dash converges to F2. So Sn plus Sn dash increasing and converges to F1 plus F2. F1 plus F2. So again by the monotone convergence theorem, so integral S1 plus Sn dash over x d mu is integral F1 plus F2 dv. Okay, and we can split the integration of a simple measure, okay, sum of simple measurable functions. Okay, so since Sn dash are simple, so Sn plus Sn dash d mu equal to integral Sn d mu plus integral Sn dash d mu. Okay, simple function நம்ம ஸ்ப்ளிட் பண்ணிக்கலாம் அப்படின்னு ஏற்கனவே பார்த்துருக்கோம். நல்லா இந்த ஸ்ப்ளிட் பண்ணிட்டேன், ரைட்? இப்போ ரெண்டு பக்கமும் லிமிட் அப்ளை பண்ணும்போது டேக்கிங் லிமிட் on both sides, we get, so left hand side is limit is integral f1 plus f2 d mu. Okay, limit of the first term in the right hand side is integral over x f1 d mu is integral over x f2 d mu. Okay, this is a theorem. So you can apply induction method to prove the following. Okay, so generalization of this. Next theorem: if f1, f2, etc. fn are non-negative measurable functions, non-negative measurable functions, then integral over x f1 plus f2 plus etc. plus fn d mu equal to integral f1 d mu plus integral f2 d mu plus and so on integral fn d mu over x. Okay, so this can be proved by induction using the previous theorem. So now we have proved the monotone convergence theorem for series and sequences. Okay, now move into the next concept. We are going to generalize the concept of one measure produces many other measures. So recall the result. If S is a non-negative simple measurable function, simple measurable function on x, then the set function phi defined on a by phi of e equal to integral over e s d mu. Okay, this set function is a measure on x. This is already we have proved. Okay, so in the place of simple function, now we are going to take the non-negative measurable function, right? The theorem is this. If the simple function is, if we replace simple function by non-negative measurable function, then we will get the same result. Okay, if f is a non-negative measurable function, function on x, right? And phi is a set function, phi from sigma algebra into minus infinity to infinity, defined by phi of e equal to d over e f d mu. Okay, this phi, the function phi is defined by this. Then phi is a measure on f. Okay, phi measure prove பண்ணனும்னா என்ன prove பண்ணனும்? First one, phi non-negative ஆகணும் இல்லையா? Phi value. Okay, for e belongs to A. What about pi of e? This is integral over e f d mu is the supremum, the definition supremum of integral over e s d mu. Supremum taken over on. Already we have proved that this integral of s is non-negative, supremum non-negative. So this value is non-negative. Phi of e is non-negative because s non-negative, supremum implies integral s d mu non-negative. Supremum taken for non-negative functions is always non-negative. So phi is non-negative. Second one, what about the measure of the empty set, right? Phi of empty set. This is equal to integral over empty set f d mu, right? This is supremum integral over empty set s d mu. Okay. Otherwise, instead of writing supremum definition, you use the following: integral over x, characteristic f, characteristic function over empty set, product f d. Okay, what is the definition of characteristic? What is a function? Characteristic function over empty set of x. If x in empty set, 1, otherwise 0, right? If x is not in 0, empty set 0, right? Empty set is treated as a subset of whole x, right? So instead of writing x not in, x belongs to empty set complement. What's the complement of empty set? It's a whole set, right? So if x belongs to whole x. Second one is the value. There is no number of the empty set. So guy empty value 0, right? Characteristic function over empty set identically 0. So what is the characteristic function over capital X? This is identically 1. So there are two characteristic functions are non-constant functions. One characteristic function over empty set, another one characteristic function over whole set. Other functions are non-constant characteristic functions. So this guy empty is 0. Okay, so all the value is 0, so integral value is 0. So measure phi of empty set is 0. Okay, then the third part. So we prove phi is countable additive. Okay, so let us take a sequence of measurable sets. It's a sequence of mutually disjoint measurable sets. Then we are going to prove that phi of E union En is summation V of En. So now we start with phi of union En from 1 to infinity, right? And this is equal to, okay, by the definition integral over. Okay, before writing these things, we will do some preliminary mathematics, right? So let us define. Fn equal to characteristic function over En into F. Okay. Then here, what about summation Fn? Summation of this, right? We define this before. Also define this. We do some basic lemmas so that we can understand this. Okay. First, claim 1. If E1 and E and F are disjoint sets, then the characteristic function over E union F equal to characteristic function over E plus characteristic function over F. Okay. So proof is very simple, right? We take a characteristic function E union F of X. This is 1 when X belongs to U, E union F. 0 if X not in E union F, F belongs to E union complement. Okay. So this is if X is in E, not in F, right? So we can split into 2. Okay. Without what? The whole X, the E, the F. Rendume disjoint, yeah. The F, right? E F complement na E complement intersection F complement. In that. Okay. So in the characteristic function, X ingeyo irunda 1, inge irunda 0, right? Okay. So now I am going to take characteristic function of E plus characteristic function of F of X. This can be written as characteristic function of Ex plus characteristic function of Fx. Okay. So this is equal to, so first one is if X belongs to E, first term 1, second 0, because if X is in E, it is not in F. Okay. The clear thing is E intersection F is empty. If X belongs to E, then X is not in F. Converse also true. So this is if X belongs to E, this is 1, right? This is first one 1, second one 0. If X belongs to F, also 1, right? If X not in E, okay, union F, that means it is not both in E union F. That is, if X not in E and X not in F, then both 0, right? So the first 2 cases can be combined. One when X in F or E or F, that means X in E union F. By the logic. Okay, X not in E means X belongs to R. This indirect, right? This is X in E or X in F. 1 if X in E complement and X in F complement, and 0. And this is an element either belongs to E or F, it belongs to the union. E union F. 0 if X in, it must be both in E complement and F complement. So this is E complement intersection F complement. This is, I can write 0, X belongs to E union F, 0 X not in E union F whole complement by the distributive law D. 1 if X belongs to E union F, 0 if X not in E union F. That is what the definition of characteristic function of E union F right? That is a characteristic function of, that is equal to characteristic function of E union F of X. So we started with characteristic function of F plus characteristic function. Therefore, characteristic function of E union F equal to characteristic function of E, characteristic function of F. So provided if E intersection F is empty. Okay, this is true for any number of elements, right? In general, if En, okay, is a sequence of mutually disjoint sets, is a sequence of mutually disjoint sets, then characteristic function of union En from 1 to infinity can be written as sum of characteristic function of En. Okay, this is the equation number 1 now, right? So okay, yeah, correct. This is 1. The equation, the statement is 1. Okay, this equation is 2. So we have assumed En are sequence of mutually measurable, disjoint measurable sets. So let us define Fn equal to characteristic function over En times F. Then Fn is non-negative. Okay, it's a product of two measurable functions, measurable. So Fn is measurable function. Okay, then what about, let us define and define G equal to, define G equal to characteristic function over union of these sets, product F. Okay, otherwise characteristic function over E unit. Define E equal to union En from 1 to infinity, and F G equal to characteristic function over E F. Okay. Now we consider, we calculate the G value. Integral over G we calculate. Phi of E. We start with phi of E, union En from 1 to infinity. This is, by the definition, this is, okay, we have set union of En is E, so this is phi of E equal to, by the definition, integral over E F d mu. Okay, this is integral over X, Chi E F d mu. Chi E F is G, so this is integral over X G d mu, right? So this is also not required. This is not required. G is unnecessary. So only it's enough. E is enough. Okay. So by equation 2, E is nothing but union of En, right? So here by 2. Integral over X, Chi E can be written as sum of Chi E En into F d mu. Take the F inside the summation, we have summation En from 1 to infinity, Chi E En into F d mu. This is what Fn, right? Integral over X, summation En from 1 to infinity, Fn d mu. Okay, what is Fn, Chi E and F? Okay, now apply the Monotone convergence theorem for series, because Fn are non-negative. So summation and integral are interchangeable. So Fn d mu. Okay, now substitute the value of F here. We have Chi En F d mu So the definition over the integral definition, okay, so definition of integral over function of over a measurable set. This is En dv. This is nothing but summation n from 1 to infinity by the definition phi of En. Okay, so we started with phi of union En from 1 to infinity and so on, and we have applied the disjointness of union En in the place here. En disjoint used here, right? Therefore, phi is countable additive, hence phi is a measure. On x, right? So for every non-negative function, okay, we have proved that. Let's remark. We have proved the statement. Let XA will be a measure space. Okay, for every non-negative real, for every non-negative measurable function, okay, there is a measure, measure on x, okay, generated by okay, that measure is nothing but phi of E equal to integral over E f d. Okay. That means every non-negative function induces a measure, right? And the conversely, the converse part also, converse part. What is the converse? If mu is a measure on mu, not mu. Okay, so every measure is induced by some function. Let's XA mu be a measure space, that is standard. Okay, for every measure, okay, I take nu. There is a non-negative measurable function f such that mu of E equal to integral over E f d. Okay, is it true? The converse is true, but with okay, subject to some restrictions. So that restriction is given in the following theorem. So Rodin encoding theorem. That's a encoding theorem. Okay, you refer. Okay, you refer the theorem. There are so many extensions for this theorem also. Still, okay, research is going on in in Rodin encoding theorem. There are so many generalizations for there. Okay. புரியுதா? ஒரு non-negative function இருந்தா அந்த ஃபங்க்ஷனோட இன்டகிரேஷன் யூஸ் பண்ணி ஒரு மெஷர் கொண்டு வர முடியும். கான்வர்ஸ் என்ன? ஒரு மெஷர் இருந்தா அது ஏதோ ஒரு ஃபங்க்ஷனோட இன்டகிரேஷனாக தான் இருக்கும் அப்படின்னு சொல்லுவோம். இப்போ மியூவே அப்படிதான் ஒரு f equal to 1 எடுத்துட்டீங்கன்னா மியூ இஸ் a measure produced by 1. ஓகே, அதான். ஸோ இந்த ராடனுக்கு தேர்வோட ஜெனரலைசேஷன் நிறைய இருக்கும். So many articles are published on the topic Rodin-Kudin theorem. Okay, the theorem enna soluduna idha okay, due to some restrictions on x a mu, every measure, every other measures, every measure is produced, okay, using the integral of some non-negative measurable function, right? Okay, idha the theorem Rodin-Kudin theorem. So in the mu ku இடையில என்ன relation? Some restriction on nu given. Yeah. Suppose mu of E0 varanda, mu of E0 at integral over a set of measure 0 is 0. In the okay. So to some the restriction eppdina idha the restriction. இந்த மாதிரி நியூக்கு இந்த மாதிரி கிடைக்கும் அப்படின்னா if mu of E is 0 then mu of E equal to 0. Such things can be produced in this way, right? Okay. Is there any doubt? Okay. Next theorem or the corollary to the previous. Okay, if f is a non-negative function, measurable function, then the set function, then if I is a, that also phi is a measure defined by phi of E equal to integral over E f d. Okay, this is a measure already we proved. Then if G is a non-negative measurable function, function on E on X, then one can use phi as a measure and you can also integrate G with respect to phi. Then the integral of G with respect to X, with respect to not X, phi. Okay, that is this. Is expressed as, right, integral of gf with respect to mu. Okay, so that the phi is called d phi. Okay, from this case, from the theorem we write d phi equal to f d. That is derivative of phi with respect to measure is f. Okay, then what's the integral phi? You look at the phi is the integral of f is the derivative of phi with respect to mu. இது எங்க படிச்சிருக்கோம்? ஃபண்டமெண்டல் தியரம்ல இல்லையா? ரைட்? ஒரு ஃபங்க்ஷன் f டிஃபரன்ஷியேட் பண்ணா கேபிட்டல் F கிடைக்கும்னு வச்சுக்கோங்க. ரைட்? g கிடைக்கும். சப்போஸ் இதெல்லாம் g இன்டெகிரல் g என்னவா கிடைக்கும்? f ஆ கிடைக்கும். அதானே இது differentiation integration inverse process yeah correct. So adha na anga pandren. Okay, we write this derivative of phi with respect to the measure mu is f, or f and phi are related by integration also by the differentiation. That's the meaning, right? Okay, ipo in the equation number 1 prove panna poren. F non negative measurable function prove pannom. நான் 3 ஸ்டேஜில் ப்ரூவ் பண்ணுவோம். ஒன்று ஃபஸ்ட்டு எஃப் கேரக்டரிஸ்டிக் ஃபங்க்ஷன் எடுத்துக்க போகிறேன், சிம்பிள் ஃபங்க்ஷன், அதுக்கப்புறம் நான் நெகட்டிவ் ஃபங்க்ஷன் எழுதுவேன். இப்போவும் நான் வந்து மோனோடோன் கன்வர்ஜென்ஸ் தியரம் தான் யூஸ் பண்ணுவேன். ஸோ ப்ரூஃப் ஆஃப் த corollary. Okay, first case, if G is a characteristic function where E is a measurable set. Characteristic function defined on a measurable set. Then, so what is the integral of characteristic function d phi? By the definition of integral, this is phi of E. Then phi of E is integral over E f d mu by the definition. Integral over E f f d mu can be written as integral over x characteristic function e f d mu, right? So here we start with integral over g d mu. G is the characteristic function. G d phi equal to this, and so therefore this is integral over x. A is g f d mu. Therefore 1 is true. 1 holds for a characteristic function if g is characteristic. If g is characteristic function. Second part is simple function program. Right? If g is a simple function, that means if g equal to summation I from 1 to n alpha I characteristic function E, where E1, E2, etc. En are mutually disjoint. Remove the set brackets. E1, E2, En are mutually disjoint such that union of Ei x equal to I from 1 to n union of E. Okay, g of x. So let us start with g of x, integral over integral over x g d phi equal to integral over x summation I from 1 to n alpha I characteristic function of Ei d phi. Okay, the lemma we proved in the last class. Here alpha 2, also here alpha 1, alpha 2, alpha 1, alpha 2, alpha n are non-negative. Okay, so it can split into m. Alpha I can be taken outside. Characteristic function over Ei d phi. Right? By the case 1, summation I from 1 to n alpha I. By case 1, this can be written as chi E I f d mu. By case 1, by 1. Discussion 1. If in the place of integrand, if you have this characteristic function, then you write this. And you take the summation inside the integral. We have integral summation I from 1 to n alpha I characteristic function Ei. F is taken out of summation, so we have this. This is equal to integral over x. This alpha I chi summation is g f t. Therefore, 1 holds for simple functions. Okay, for simple functions. Simple functions. So now we prove the general case for non-negative measurable functions. G is non-negative measurable function. If the non-negative measurable function immediate analysis by approximation theorem, there exists a sequence of simple non-negative simple measurable functions. Simple measurable functions such that write the symbol Sn converge, increasing and converge to Fg. Right? By monotone convergence theorem, right? Limit n tends to infinity, integral over x Sn d mu equal to integral over x g d mu. In the place of, we write the integration with respect to phi, right? D phi. Right? Since Sn increasing and converged is g and f non-negative, so Sn f is also increasing and converged to fg. Okay, once again by the monotone convergence theorem, again by MCT, limit n tends to infinity, integral over x, Sn f, here integration with respect to mu, with integration with respect to phi MCT phi apply mu apply integral over x, right, gf, increasing and converge to pointwise, increasing pointwise, convergence pointwise, gf d mu. Okay, so now by discussion 2, that means the result is true for simple functions. So for each n, integral over x Sn d phi equal to integral over x Sn f d mu. Applying limit on both sides, so we get this limit of this integral Sn d phi is integral over x, right, g d phi, integral over x, Sn phi converge to gf, so integral Sn f d mu is gf d mu. That's all. So one goes for non-negative functions. Hence the result, right? So any doubt? Is there doubt? Abhinisha, Navina, Niveda, Sasikala, Yuvasri, Aisha. Mute பண்ணிக்கங்க நவீனா. வேற ஐசக் புரியுதா?
எஸ் சார், புரியுது சார்.
ஓகே, எதுவும் டவுட் இல்ல?
நோ சார்.
ஓகே அபினிஷா, ஓகே. வேற என்ன பேர் நான் சொல்லல, எனக்கு எந்த பேரை சொன்னாலும் ஞாபகமே இல்லை. சுந்தேஸ்வரி, சுந்தர், தாரகை, வாசுகி எல்லாம் புரியுதா? உங்க பேக்ரவுண்ட்ல எந்த ஒரு சத்தமும் இல்லை அப்படின்னா நீங்க அன்மியூட் பண்ணுங்க, அன்மியூட் பண்ணி பேசுங்க. எஸ் சார், ஓகே, புரியுது. டவுட் இருக்கான்றது எஸ் சார் சொன்னீங்களா? வாசுகி எஸ், தாரகை எஸ் சொல்லிட்டீங்க. புரிஞ்சதான்னு கேட்டது இல்லையா? ஓகே, இந்த கிளாஸ்ல நடத்தின கூட படிச்சு புரியலைன்னா கோடு போட்டுக்கோங்க. கோடு போட்டு கொண்டு வந்து எந்த ஸ்டெப் புரியலை, ஏன் எழுதுறோம் அப்படிங்கிறதெல்லாம் நீங்க கண்டிப்பா தெரிஞ்சிருக்கும். சரியா? புக்கை ரீட் பண்ணி பாருங்க டைம் கிடைக்கும்போது. ஓகே, கண்டினியூ பண்ணுவோமா? அடுத்து முக்கியமான ஒரு ரிசல்ட் சொல்ல போறேன். ஓகே, இட்ஸ் a contemporary of Fatou's lemma. Sorry, monotone convergence theorem, that is Fatou's lemma. It's okay. Now we start discussing one important lemma, which is Fatou's lemma. Okay, so we are going to use monotone convergence theorem to prove Fatou's lemma, but we can also prove independently this lemma. Okay, we can prove Fatou's lemma independent of monotone convergence theorem, and after that you can prove monotone convergence theorem using Fatou's lemma. So ரெண்டுமே ரெண்டு சைடு. Monotone convergence theorem ku independent proof irukku, Fatou's lemma ku independent proof irukku. Okay, one can prove using the other also. Okay, Fatou's lemma independent proof எப்படி இருக்கும்னா, monotone convergence theorem என்ன methodology யூஸ் பண்ணுவோம் almost same ஆ இருக்கும், but okay, there may be a small change in that. Okay, so a theorem about limit infimum of f. Right? Suppose f1 is a sequence of non-negative measurable functions. It's a sequence of non-negative measurable functions. Then limits integral over x, limit infimum and tends to infinity fn du is less than or equal to limit infimum and tends to infinity integral over x fn du. Right? The theorem state conclusion என்ன நடந்திருக்கு சொல்லுங்க. fn ல இருக்கிற limit infimum வெளியில வந்துருச்சு இல்லையா integration. இப்படி வெளியில வரும்போது inequality arises. You can take out of this limit infimum out of this integral, then you will get inequality here. Okay? Limit infimum fn calculate பண்றது point wise தான் கன்வெர்ட். supremum calculate பண்ணா அப்புறம் infimum then supremum calculate பண்ணோம். That sequence right side ல இருக்க numbers. Okay? லெஃப்ட் சைடுல இருந்து லிமிட் இன்ஃபிமம் fn கால்குலேட் பண்ணும்போது ஃபங்க்ஷனுக்கு கால்குலேட் பண்ணும். இங்க லிமிட் இன்ஃபிமம் நம்பர்ஸ்ல கால்குலேட் பண்ணும். இதுதான் டிஃபரன்ஸ். இது ஒரு எஸ்டிமேட்டா யூஸ் பண்ணலாம். லிமிட் இன்ஃபிமம் நம்பருக்கு கண்டுபிடிச்சு பண்ணும்போது. So proof is very simple using monotone convergence theorem. So define Gn equal to infimum for all k greater than or equal to n fk. Right? What is the limit? G. And f equal to f is the limit of Gn. What is the limit of Gn? Limit of infimum fn, that is limit infimum n tends to infinity f. So we prove that integral over x, in the place of limit infimum fn, you take f d mu, which is less than or equal to infimum, limit infimum n tends to infinity, integral over x, fn d mu. That is, we prove that limit of infimum k greater than or equal to n, integral over x, fk d mu. Okay, so now we already we have defined this Gn is infimum fk. So from that, this is 1 here. From 1, Gn of x, Gn always less than or equal to fk, k greater than or equal to n. So implies integral over x Gn d mu less than or equal to integral over fk d mu for all greater than or equal to n. That means integral Gn is the lower bound of all integral fk. Right? What about infimum integral fk? D mu. Infimum taken over all k's here. Infimum taken over all k greater than or equal to. This number is the greatest lower bound of this integral fk. The integral Gn d mu is a lower bound. Okay, so which one is smaller? Lower bound is smaller. Greatest lower bound will be comparatively bigger than limit infimum. Okay. புரிஞ்சுதா அது? புரிஞ்சது தானே? ரெண்டு நம்பர் கம்பேர் பண்றேன். ஒன்னு லோயர் பவுண்ட், இன்னொரு கிரேட்டஸ்ட் லோயர் பவுண்ட். எது பெருசா இருக்கணும்? கிரேட்டஸ்ட் லோயர் பவுண்ட் பெருசா இருக்கணும். ஓகே, ஓகே, இது ஒரு ஈக்குவேஷன் நம்பர் 2 எடுத்து. இப்போ Gn again by the definition of Gn, from the definition, right? Gn definition from the definition of Gn. Gn definition G1 என்ன infimum overall k greater than or equal to n, k greater than or equal to 1 fk, that is infimum of f1 comma f2 comma etc f and so on. G2 எப்படி இருக்குது infimum k greater than or equal to 2 fk, this is greatest lower bound of f2 f3 etc f and so on. Okay, this is set to first set, second set. எந்த செட் பெருசா இருக்கு இந்த இடத்துல? இது f1 இன்க்ளூட் பண்ணிருக்கோம், இன்க்ளூட் பண்ணல. இப்போ முதல் செட் தான் பெருசு. இன்ஃபிமம் பார்க்கும்போது அதிக நம்பர் இருக்கும்போது லோயர் பவுண்ட் குறைச்சலாக சான்ஸ் இருக்கு இல்லையா? கிரேட்டஸ்ட் லோயர் பவுண்ட் குறைச்சலாம், ரைட்? அதனால இந்த டெஃபினேஷன்ல என்ன எழுதலாம்? G1 less than or equal to G2, G3 F3 ல இருந்து ஸ்டார்ட் பண்ணுவோம். அதனால சப்போஸ் கிரேட்டஸ்ட் லோயர் பவுண்ட் F2 ஆ இருந்ததுன்னா F2 மிஸ் ஆகும்போது இன்னும் கொஞ்சம் அதிகமாகும்னா G2, G3 less than or equal to. Okay, so what about the limits? N tends to infinity Gn, F எப்படி இருக்கும்? Supremum of Gn, supremum taken overall இல்லையா? So this implies since G equal to this implies G, right? That is Gn less than or equal to F, that is G1 less than or equal to G2 and so on, everything less than or equal to F, and Gn converge to F. So G1 G2 are monotonically increasing and converge to F pointwise. So by the MCT another limit n tends to infinity integral over x Gn d mu equal to integral over x F d mu. Okay, so now start with integral over x, so that is limit infimum Fn, n tends to infinity d mu, limit infinity Fn is integral F d mu. This is limit n tends to infinity integral over Gn d mu. This is equation number 4 from 4 implies, right? From 4. Okay, and 3 says integral Gn less than or equal to infimum integral Fk, that's equal to limit n tends to infinity infimum k greater than or equal to n integral Fk d mu by 3. This is equal to limit infimum n tends to infinity integral Fk d. எந்த இடத்துல less than or equal ரைஸ் ஆகுது? இந்த இடத்துல. Therefore, so that's all, right? So we get the factors. So we started with integral limit infimum Fn, so we ended with integral over x limit infimum n tends to infinity Fn d mu less than or equal to Fn limit infimum n tends to infinity integral of Fn n d mu. Right? That's all the factors.